Hello, everyone, and welcome again to your channel, Math Made Easy. In today's session, I'm going to go over a new topic, that's the centroid, okay? So what are centroids and how we are going to use them? A centroid, well, let me back up and say, if I have a plate or this piece of paper, paper is flexible, so it won't work. But let's say we have let's assume this is a rigid, there are no holes inside. And I have this ruler or that, palette, and I would say find a point on this thing that when I hang it by a rope, it would stay horizontal. It won't turn like that or turn like that. It stays horizontal. So where is that point? This point is called the centroid. In fact, if it's the same material, the same thickness, sometimes you also call that the center of mass or the center of gravity. So all these three terms would be the same if I have a plate made of the same material and the same thickness. But when we say centroid, we are not looking at a plate or something, we are looking at an area usually, okay? So this area, suppose that it was rigid enough. Where should I hang it? If I hang it through just one point, where would that point be? In some other cases, you can see, for example, you have a light fixture or something, and you attach it at, say, 3 different locations. So suppose you have a circular thing like that, and for some reason, you want to hang it through several points. Usually, it's 3 or 4. If you notice, you will use, say, a point here, and then you turn 120 degrees and another 120 degrees in such a way that these 3 cables or 3 ropes or whatever, they meet at a point, and that point would be exactly over the center of the circle. If it's not exactly on the center, you will see that the lighting fixture is turning one way or another. So at the end of the day, for a circle, of course, we know the center is the centroid. We don't have to worry about that. Some rules. We tell you if there are 2 axes of symmetry. For example, if I draw any diameter here, that's an axis of symmetry, right? And then I pick another, it can be like that, another diameter. Since they intersect at the center is the centroid. Likewise, if I have a square, it's where the 2 diagonals meet or the 2 mid sides meet. Same thing for a rectangle and so on and so forth. So how about a triangle? Yes, some who did geometry know the answer. But let me give you an easy way to find the centroid of these simple shapes. Okay? I'm going to draw a rectangle. I mean, again, not to scale, I'm not going to use that. I'm going to just draw about a rectangle here, and then a triangle in this direction. So I'm using the bottom left corner as a right angle, okay? And I will assume this is the origin. So this is the x-axis, this is the y-axis for all of them. And then, so that's a triangle. This is a second-degree parabola. So y equals x squared or something like that, plus or minus. And this is maybe a third-degree parabola, and so on and so forth. So this is second, this is third. So this method will let you know where is the centroid without thinking. I'm going to write area. And this would help you in other classes, by the way. Uh, know the answer right away, so to speak. And then I'm going to refer to the x coordinate of the centroid. We call it x bar. And also the y bar. Now, maybe I wanted to add another column here called n, and n here is the power, right? When you say x to the power of n, so n is the power. If you have a horizontal line, that's the rectangle, right? The rectangle has a horizontal line here, has a straight line there, has a second degree parabola, third degree, 10th degree, and so on and so forth. What is n here? Meaning y equals something times x to the n. What would n be? I hope you're not confused. It should be 0 because that's a horizontal line. The power of x is 0. You keep changing x and y is the same. So y is not a function of x. So here the power is 0. If it's linear, you know, y equals negative x, for example, or negative 2x or negative 1/2 x or whatever, but it's x to the first power, right? It's a straight line, so first power. Second degree, second power. Third degree, third power. 10th degree, 10th power. Okay? Now, if the base is b for all of them, and the height is h for all of them, the area here becomes BH over n plus 1. 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 N plus 1 here is 1. So B times H is the area of a rectangle. N is 1. So 1 plus 1 is 2. BH over 2, or 1/2 base times height, is the area of a triangle. A second degree parabola, its area is 1/3 BH. A third degree, 1/4 BH. A 10th degree, 1/11 BH. And it doesn't matter what degree you have, you can easily find the area. And you say, okay, but I'm more interested about the centroid. Well, the centroid, the equation of it, okay, the centroid is where along the base is my x bar. So here, 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 here. Where is x bar in all cases? It's b. Let's write it on the top. B over n plus 2. So b, 0 plus 2 is 2, so b over 2. Yes, it's in the middle, b over 2, 1/2 b, absolutely. For the triangle, it's b over 3. 1/3 from the right angle, meaning 2/3 from the other direction. Because that's a common mistake. We give a problem where we have a triangle like that, and we say, for example, the base is 9, and let's say the height is 4, or whatever, and the students would say, two mistakes, first of all. First, they say it's 1/3, so it's 3. No, it's not 3. It's -6 if that's the origin. And if that's the origin, it's 6. Okay? So first of all, you need to know where the origin is, and then you relate to. And the second thing is, where is my 90 degrees? It's 1/3 of the base from here. Here it's on the left. So this would be b over 3, and that's 2b over 3. b over 4, b over 5, and so on. You just add 2 to the power, and that's it. For the y bar, it's a little tricky. It's not an easy equation like that. Okay? It's, well, I don't have to say here. B plus 1, I'm sorry, h plus 1, because in the y it's the h, right? H plus 1 over 4n plus 2. So if n is 0, what did I say? No, n plus 1 over 4. I said h. N plus 1 over 4n plus 2 times h. So if n is 0, the numerator is 1, the denominator is 2, so you get h over 2, which is the same for a rectangle. It's half the base, half the height, of course, because these are axes of symmetry and they intersect at that point. If it's a triangle, n is 1. So in the numerator is 2, and 4 plus 2 is 6. 2 over 6 is 1/3, so h over 3. So for the rectangle and the triangle, it's the same thing. 1/3 base, 1/3 height. Half base, half height. But once we move higher than that, it becomes different. So if I go to the second degree parabola, n plus 1 is 3. And if n is 2, 4n is 8 plus 2 is 10. So 3/10 h. This is 3/12, but this is 3/10. When you go to the third, and then we'll stop, n is 3, so n plus 1 is 4, and 3 times 4 is 12, plus 2, 14. 4 over 14 is 2 over 7 h. And that's it. Okay? So that's for lines like powers of n, meaning horizontal line, straight line, second degree, third degree, parabola, and so on and so forth. Now let's move, and we said for a circle, I know it's the center, so that's easy. If that's the origin, then x bar equals y bar equals 0. If that's the origin, then it's r, the radius, is the x bar, but 0 is the y bar, right? It's the intersection of, and so on and so forth. But what if it's not a full circle? It's half a circle or a quadrant. We are not going to go, well, we can, but I think for now, we are going to use either half a circle or a quadrant. Well, I didn't do, it doesn't matter. It's really not that important. What I'm going to do here, let's do semicircle here. Oops. Well, you get it. And then maybe uh-oh. So let's make it 2 centimeters. Doesn't have to be exactly 2, so let's, oh, this is not easy. I think I don't have, let's do a quadrant, just a quadrant like that. So let's say, for example, this is the origin, and this is R. Same thing, this is the origin, and this is R. We can use, I think we can use, not I think, I know we can use integration to find that, but that's probably, I will use it, maybe you can use it today, but for now, I'm going to say, here is a quadrant. So the area, of course, is pi r square over 4, because the whole circle is pi r square. If it's a quadrant, a quarter of a circle, then it would be pi r square over r. According to what we did, the x bar would be negative, but the y bar would be positive. So x bar, y bar. X bar would be negative 4 pi, I'm sorry, 4r, why did I say, over 3 pi. And the y bar is the same thing, but it's positive 4r over 3 pi. If I have a semicircle, this one, specifically this one, and that's the origin, of course, x bar would be 0 because now this is an axis of symmetry, right? So the area would be pi r square over 2, x bar would be 0, and if it's a half a circle, y bar would be 4r over 3 pi. The same. Here is the centroid. Here is the centroid. They are at the same height here. Now, we can use, well, I think I'll defer that to the next lecture. I wanted this to be a short one, just to give you where the centroid of very common shapes that you will encounter are. So for a rectangle, a triangle, a circle, second degree parabola, I don't think we will encounter third degree parabola, but any kind of a parabola is easy now. And then for a circular shape, I need to find the centroid if it's an ellipse, not a circle. So let's say, just give, if that was a quarter of an ellipse, oops, and let's say this is A, this is B, and that's an ellipse. Well, I should have drawn it the other side, so both would be positive, but it's very similar, okay? So the area would be pi AB over 4, because a circle is a special case of an ellipse where both axes are equal. The semi major axis and the semi-minor axis, if they are equal, they become a circle. So instead of saying r times r times r times pi over 4, we say a times b times pi over 4. Accordingly, this would be negative 4a, not r, 4a over 3 pi, and that would be 4b over 3 pi. Pretty straightforward, right? And that's basically all what I wanted to cover today. I want you to be familiar with these simple shapes because next time we are going to attach many of those. So we may have a rectangle attached to a circle, or a semicircle on one side, and then on top of it, it has a triangle. On the left-hand side, it may be attached to a quadrant of an ellipse. And I ask you, where is the centroid? So we learn how easy we can find these centroids for composite shapes. These are simple shapes, so you don't need to do anything. You already know the answer, okay? And maybe at the end, instead of giving you, if that's not a plate, so suppose that's not a whole rectangle, but it's a rectangular frame. Where is the centroid? You will see that for a rectangle and a triangle, it's the same, but for a circle, it might be a little different, and not a circle, a semicircle or a quadrant. We'll talk about that, and then I will barely touch on something or a corollary of a theorem known as Papus theorem that is extremely helpful. You would love it, I'm sure, once we go over it next time. Thanks for your watching, and have a great day. Hope to see you soon.